Welcome to this tutorial in which we'll be solving partial differential equation PDEs with Python. In an early tutorial I show you how to solve and to implement finite elements, so to solve partial differential equation in 1D from scratch. In this tutorial what we will be doing is something similar, but instead of doing everything from scratch I'll be using a library, Polyfem, to solve the PDE. The main goal of this tutorial is show you how easy it is to set up a PDE problem, a finite element problem, using this library and to get a solution really quickly. I will try to show you how to do that by doing live code. So if you remember in the 1D tutorial what we did, we started by specifying what is the domain. And in 1D we are just this segment 01, in 2D we will have a polygon as a domain, and in this case it's this weird shape. Then one of the first things we did for our segment in 1D was decompose it into elements. So into this tiny segment, which was decomposing the long segment. In 2D we cannot really decompose the domain into segments. What we'll be doing is discretizing the volume, discretizing this domain into triangles, and then as I show you in 1D, this is not enough for solving the PDE. We need to pick which PDE we want to solve. So since this is something a bit more interesting than just having a diffuse like Laplace, we want to solve elasticity. So elasticity is just a PDE that describes how an elastic body deforms. And then, similarly as the 1D example, we need also to specify some boundary condition, which is what we want to do, what kind of load or displacement we want to apply to our domain. And for this simple example, we want to fix one side and then pull or move another side. So how actually can we do it in Python? Well, it was already introduced, but I will be using some libraries, so NumPy for linear algebra, and important here is all this library we've been developing. NumPy is kind of the glue. You can move data from one library to the next one by just using NumPy matrices. And this is not only cool because you can all use this library independently, it's also cool because you can plug other things, like for example PyTorch or TensorFlow if you want to do machine learning. So I'll be using NumPy, Meshplot for the plots, and also this library works from NumPy. And finally, the two libraries which are more computationally involved. One is while meshing, which is the one that creates that's used to create meshes, and the other one is Polyfem, which is the library which we'll be using to solve finite element. So let me import these libraries. And now, well, we need the domain, and this is a part which is not super interesting. So I have a set of segments in 2D and vertices connecting them to define our domain. So let me execute that and show you how our domain looks like. So we have in black the segments, and we have some red dots here showing the endpoint of the segment. So we have this domain, and this domain is, well, just created this simple shape using Illustrator. And now, well, the first thing we want to do is to do mesh this domain to generate a triangle mesh. So for doing that, we will be using while meshing. So in this case, it's really simple, just one call. So we want to get the vertices and the triangles. We'll be ignoring for the moment some optional parameter. I will go there in the very end of this tutorial, and we can just do while meshing dot triangulate data. We want to triangulate some data, and what do we want to triangulate? Well, the vertices and the line we had before. So let me just execute this cell, and in a second here we get the triangulated domain. So we can plot, we can use Meshplot to visualize. So we want to visualize the VS and the trees. We execute this cell, and oops, this is what we get. Let's try to get also the wireframe to see what's happening. So we can enable the wireframe by just setting it to true. So now we get the wireframe. And now you can see here, let me go back and forth to recenter the cell. You can see that in fact our domain is there, but there is some other boundary around. So in a previous lecture, we explained how this while meshing library works, and the idea is that we're not only meshing the actual domain, which you can see here, but you are meshing also a little bit larger and bounding box around. And if you actually want to retrieve the domain, well, what you need to do is specify an additional flag here to cut or to remove everything that's outside, and this is just cut outside true. So here in this case we are remeshing everything and we are cutting what is outside, and now we get this nice triangle mesh. And there is a couple of things I want to specify here. Is that the first one, if you look, the sampling on the edges was kind of random and arbitrary, and white meshing automatically resampled the edges, so it doesn't really respect the boundary points exactly. And this is great because, for example, the arc here has many nodes, and the actual mesh has less, and it looks nicer. And the same hold for, I don't know, the top. It has few nodes, but it automatically adds more uniform space. So now we got this nice mesh. So this is the first step of our finite element simulation. So now the next step is to actually start to set up the problem and set up the finite element solver to actually solve the finite element. So one of the important things about finite element is that we want to specify the boundary condition. This is super important to specify the problem. And this is one of the things which is usually complicated to do. And one way to do it, if you ever use a finite element software, is just have a fancy UI where you can click on Faceit and on Paint on some of them to retrieve them. So the way it works in Polyfem, there are two ways. One is the default one, and what Polyfem will be doing is automatically setting some number, the number of the side set, to facets or edges in this case, since it's 2D, touching the boundary. So we will have 1 for the left, 2 for bottom, 3 for right, and 4 for top. Everything that's touching the bounding box up to some epsilon will be automatically assigned with that. Another way in Polyfem to specify boundary side set and boundary condition is to use a lambda function. We will see that in a next tutorial. So if we want to use Polyfem, well, the first thing we need to do is to just create the solver. So here I'm just creating a solver, and now we can just load the mesh inside the solver. And here the mesh is the mesh we just created before, which is just the vertices and the triangles. And then another thing we want to do is, okay, let me move that in the same cell so it's more organized. So now we load the mesh. Here we can see, for example, the size of our mesh, which is kind of on the 100. And now if we want to get the side set which are being created automatically, well, we can just ask Polyfem to give them to us. So we can get the side set points, the side set lines. In this case, there will be lines, and then the side set value, but just asking the solver to get the boundary side sets. So this step is usually useful only in the beginning when you're solving the problem. Once you are sure about your side set, there is no need of doing it anymore. But it's really important because there are always tiny problems with the side set, you're selecting the wrong faces, etc. So in this case, we are relying on the default. So what I'm doing here, I'm getting these side sets, and then I'm just creating some color and selecting the side set. For example, E1 is the side set corresponding to 1, E2 is the side set corresponding to 2, etc. And then I'm just plotting a point in the middle of the edges here, red, green, blue, and black, from 1 being red, 2 blue, and etc. So if I zoom out in the picture, let me maybe go back to the cell so it's recentered itself. So if we look here, we see that the side set 1 is here in the red side, the side set 3 is on the blue side. So the initial problem, what we wanted to do is to fix the red one and pull the blue one, which means we want to fix side set 1, which is the one corresponding to the red one, and pull side set 3. And for the black and green, we just don't want to do anything, so we will leave it alone. So now let's move on and try to specify this problem. So to specify the problem in Polyfem, what we need to do is to create some settings. Settings equal polyfem.settings. And then what we can do, okay, now we have the settings, and then we can also create a problem. And the difference between the setting and the problem is the problem kind of specify what we want to solve, and the problem is more encapsulating the boundary condition. So for example, we want to solve the PD, which is PDs dot, for example, linear elasticity. So there is a bunch here of PDs pre-implemented, you can just pick any of those. So for the moment, we just want to do linear elasticity. So we create the problem, we create the setting, and now, well, inside the setting, we can specify which material we want to solve. So setting dot set set material parameter. So for example, we want to set the Young modulus to something like 21,000, which again, this is a number. You just go on Wikipedia and find it. This is the material parameter corresponding to stainless steel, and there are always two material parameters. One is the Young modulus, which is E, and the other one is the Poisson ratio. And in this case too, the Poisson ratio is called nu, and in this case I will also pick the one coming from stainless steel. So here I want just to do a tiny parenthesis. If you don't know about the material parameter, it's fine. Just don't pick something random, because some are not physical, so you will get garbage out of it. If you know about material parameter and what they are, you also know they have units. So the whole library Polyfem is unitless, in the sense that you need to be sure that everything is consistent in the correct unit. So if your mesh is in meter, you need to be sure that your material parameter is also in the same corresponding unit. So the unit is not really important as long as everything is consistent with each other. So now we pick which material we want to solve, and now we are ready to set the boundary condition, and the boundary conditions are set on the problem. So we do problem, for example, we want to set the displacement of the side set 1, which was the red, and we want to set it to 0, 0, and then we want to set the displacement of the side set 3, which was the blue part, to something like 10. We want to pull by 10. So if you remember, the bounding box of the model was around 100, so 10 is like 10%, so we are pulling quite heavily. And then finally what we need to do is settings dot problem equal problem. Just set the problem inside the settings. Okay, so this is more or less setting up the material and setting up the boundary condition. This is done again with 5 lines of Python. It's pretty straightforward. So this is, if you want to copy this notebook and do implement your own stuff, this is usually the only part you will be changing. The creating the mesh, etc. is always the same. Loading the mesh is always the same. What you want to change here is how the problem is specified. So now we have everything set up. So the only thing missing is to solve the problem. So we need to load the settings. So it's the solver dot settings. Just load the settings we just created, and then we can just do solver dot solve. Okay, there is a lot of log here happening. At the end we get a solution out of it. So now, well, we solved the problem. Let's see if we get something meaningful out of it. So what we want to do is now get the solution. And now there is something technical here about finite element. So the solution of finite element, as we saw in the tutorial, is a continuous function. So if, like in this case, we are solving a piecewise, we're using linear element, the solution is piecewise linear. So when we're using OpenGL to interpolate the data, if we're interpolating the data inside a triangle using piecewise linear interpolation, everything is correct and cool. But if we're using higher order element, like we did in the tutorial, the solution will be piecewise quadratic. So using linear interpolation is not good. So what Polyfem does automatically is oversample every triangle a little bit more to provide an accurate and correct visualization of the solution. So when you're getting the solution out of Polyfem, what you're getting is a solution sample on more dots. So what we will be getting is some solution points, solution triangles, and the solution itself, which in this case will be a displacement. And to get it out, it's just solver dot get sample solution. So we can get the sample solution out of it. Another important physical quantity related to the physics, to the elasticity model, is the von Mises stress, which kind of tells you how much the material is stressed. So this will be called Mises, and there is another optional parameter we can ignore, and we can just ask solver dot get sample Mises AVG. So the reason why there is two versions, one with AVG and one without, is that the foam easy stress depends on the gradient of the solution, and since the solution is piecewise linear, the gradient will be piecewise constant and it will look awkward. We will have all these triangles separated. So a common way to make the result look better is just to average the solution around vertices to get a smooth result. So let me get the solution out of it, and now we can just plot the solution itself. So we can just do let me save the plot, so we can do mesh plot dot plot. And what do we want to plot? Well, the solution points, the solution triangles, the mean stress, and now we want, for example, return. We want to get the plot saved there. And let me just show you this, and this is how it looks like. So if we want to compare this solution we just get with the initial solution we had in the very beginning, we can add edges to the plot, and we want to add the input edges. And here, I don't know, it's not super visible, but there is some black line appearing. Let me zoom. And if you note, there is no difference between the black line and the colorful one. Well, and it could be, I don't know, something is wrong. The reason why there is none is because we are not using the displacement. We're just visualizing the point. So if you actually want to displace the mesh to apply the displacement to the solution, what we need to do is to just sum it up. And this is nice, and we're just using here NumPy matrices to just sum, and now we see we have something nice and fancy, and there is a clear displacement here. So I show you in the previous tutorial that we can do higher order elements. So what if you want to, if you are unhappy with this piecewise linear solution, you want to have a piecewise quadratic solution? Well, this is extremely simple. We can just go here and add another parameter, which is the discretization order, which is the order of the finite element. You can just write 2 here. So let me re-execute this cells, solve again the problem, get the solution out of it, and now you see that everything looks a bit nice and smoother because now we get a quadratic solution out of it. And I just want to show you another cool part about Polyfem is that, well, now we have this large displacement in the mesh. So if you know a little bit about physics, you know that this is not physical at all. Having this 10% displacement and using a linear material model is bad. So if you want to use a nonlinear material model where there are plenty, the easiest way is just write NON in front of that, and this will default into using the Hooken material model. So if I re-execute this cell, I mean, I'm not changing anything. Now instead of doing a simple linear solve, we're just doing a Newton nonlinear solve, but we get now this solution, which is now more physical. If you ever did some finite element simulation, finite element testing, or open any textbook, you may have recognized the mesh or the domain I'm using. So this mesh or domain is just 1/4 of a classical domain, which is called the plate or plane with hole. So this is just a domain, a rectangular domain with a hole in the middle, and it became popular because it's a classical test example. And the example here we have this plate with hole, and we just want to pull it to apply some force left and right. And for efficiency and symmetry reason, there is no need of solving the problem on the whole domain. We can just solve it on a 1/4 of the domain, which is this tiny piece here on the bottom. And then what we want to do is to apply something that's called symmetric boundary condition. So this is just a fancy word for saying, for example, this line here needs to be fixed on X and it can move on Y, and this line here needs to be fixed on Y and can move on X. So what if we want to do this real plate with hole in Polyfem? So here again, the mesh is the same. The only thing we need to change is the boundary condition. So let's go back here and create a new problem. And now instead of setting the displacement here, we don't want to set any displacement. So let me just command that. And since the plate with hole here is a fancy thing, instead of setting the displacement, we can set some force. So we want to set some force on that side set. And in this case, we want to set a lot of force since it's steel, something like 50,000. And then the other important thing is in these two yellow parts we had before, we want to set them to into some symmetry. So what we want to say is that the side set 1, which is where we were applying the force, should be symmetric on X. So this is problem.set X symmetric, and which one is the one, and then we want to say problem dot set y symmetric, and which one is the y. If you remember, there was one left, two bottom, sorry, two top, three right, and four bottom. So the one we want to be symmetric is two. Okay, so now we can go back and solve everything, and again it takes some little time, and now we can get something, a solution here, and this is how it looks like. So you see it doesn't move on x and y. I think we just applied too much force, so let me go back and remove a 0 here. Oops. Okay, re-execute, create a new problem to be sure everything is nice and fresh. So now it looks better, and you see on the bottom here it just slide across this boundary. Also here on the left it slide across the boundary, so it was fixed, it stays there, but it was allowed to shrink a little bit. So this is the full plate with hole example. So when we show you the theory and the idea behind the triangulation algorithm we had, we went great length to explain to you that we can actually create higher order meshes and meshes which actually reproduce curve inputs. And this plate with hole and this mesh we have here is, well, its piece is linear. So the circle we have here is not a nice perfect circle, it's just some segment. And in fact, I told you in the very beginning that we generated these meshes using Illustrator, and Illustrator can generate curves. So I happen to have the real SVG model. So what we can do, instead of triangulating data, we can try to triangulate the SVG. And I will just load the SVG I have on my disk, which is plain hole.svg. And if I just run the same thing again, while it takes a little bit longer, we end up with this mesh. And okay, let me go back and again. So, and you see here it's completely different. We don't have anymore this kind of fan thing next to the curve, but now it looks even worse. And the reason why it looks worse is that because this higher order mesh is in fact has all curve element here where it's chopped, where it's worst. And mesh plot cannot support visualization of higher order meshes. And another thing here, we are getting only the vertices and the triangles out of it. What we want to do is to get everything out of it, so we can exploit additional parameters. So one is the nodes, which will be the higher order nodes, and then the other one would be the F nodes, which are the association between the nodes and the faces. So let me rerun it. And if we actually want to see where these nodes are, what we can do is do return plot true. So we want to return the plot, and then we can try to visualize. These points, and we want to visualize the nodes, for example. Okay, I think they're tremendously small, so we just want to do shading, and we want to change the point size. Point size, we want to set it to be large enough. Yeah, maybe a little bit more, 5. And now you see the triangle that should be curved. Now they have these red dots showing that this will be a higher order. So in this case, there will be cubic triangle. They have this additional 2 nodes per every edge and 1 node in the middle. So now we will have this curved triangle. Unfortunately, we cannot visualize them directly. So another thing I want to show you here is this nodes. For example, this is just a NumPy array of integers. So this is another way, place where everything is kind of communicating through NumPy. So all the data here I'm passing around, those are just NumPy data structure and standard. There is no need of doing any conversion if you want to pass it to another library. So how we can actually use that in Polyform? This is really easy. Instead of just loading the mesh in the triangle, we can just set, instead of the mesh, we can set I. Okay, let me just execute the cell. So we have it. So we can do solver.set higher order mesh. And what do we want to set for the higher order mesh? Well, the vertices and the triangles we had before. And then we want to also load the nodes we just computed with while meshing, and the association between the faces and the node, which is this F nodes. So I'm just loading the mesh, and the bounding box is the same. And now the rest remain exactly the same. So we can just get the boundary side set here, and the only difference is that well, there will be less segments here and different triangulation, but we get exactly the same color we were having. We can set the problem again, the boundary condition, same as before, and then just call the solver. And in this case, we'll be using a cubic element for the geometry. So the geometry will be this beautiful curve mesh, and we'll be using quadratic element for the finite element space. So when I explain to you how to implement finite element, I show you this idea of the geometric mapping, and the geometric mapping was linear in what we had. Now it will be cubic. And I also show you that you can have a linear geometric mapping with a cubic function, and in this case we have something different. We have a cubic geometric mapping with a quadratic function. It doesn't really matter. And now this is where the sampling gets more important. So now the geometry and the solution are not linear anymore, so it's really important to sample this triangle a little bit more to see something more meaningful, and this is the result we get out of it. So now the curve is nice and smooth. And in fact, if I go back just to show you something interesting, if we go back and use a linear element and solve the problem again, well, the solution of the finite element will be piecewise linear, but since the geometry is higher order, there will be no piecewise linear approximation here of the curve. The curve now doesn't come from the solution of the finite element, but comes from the geometry. Okay, thank you for listening, and that's it on the finite element simple example. Final tutorial on finite element and meshing. So this is the last tutorial, and I will be using all the library we show you during this course. So we call it final example, ultimate example. So I will be using NumPy for the algebra, some math, for doing some basic operation, then libigl or IGL for loading data and manipulating geometrical data, while meshing for meshing, and Polyform for the finite element. So I showed you before an example in 2D, and since this is the ultimate example, I will be showing you an example in 3D. So let me just import this library by just executing this cell. Focus. Okay, so now I executed the cell. So the first thing we want to do is to just get a mesh from the D. So this will be the domain we'll be solving the PDE. So in this case, we want to have an ultimate example. So I selected a mesh from the ABC dataset, which is full of CAD models, so mechanical piece, and this is how our mesh looks like. So now the first step in finite element is always try to get that mesh out of it, and in this case, it will be a tetrahedral mesh. So what we want to do is to create a tetrahedral mesh, and this is something a little bit more complicated than a triangular mesh. So for this, we want to use while meshing, and we want to use the tetrahedralizer. So there are two ways of using the tetrahedralizer. One, we can just tetrahedralize an input file, or we can use this more advanced object-oriented way, which just creates a tetrahedralizer and then set a mesh and then call the tetrahedralize function. And the big difference between the two is that once we call the tetrahedralize function, we just get the mesh of the whole volume, including also the bounding box around, and then we can use different strategy to extract the tet mesh out of it. So for example, we can just call get tet mesh, which uses the winding number, or we can use the float field strategy if you prefer. But the post-processing, so extracting the tet mesh out of it, is something extremely cheap, and this is why it's completely separated. So now we are waiting a little bit to generate the tetrahedral mesh, and then this will be the tetrahedral mesh of the whole volume, and then what we can do is just extract the tet mesh with one command. And if we are unhappy with the extraction, we can try and experiment with different one without need of waiting the whole tetrahedralization to happen. So another thing here is that for timing reason, I'm just stopping the quality of the tet mesh to be maximum 30. So normally the default is 10, so here we are allowing for an element with a little bit worse shape. So I think it's almost finished. It also looks lower because I'm running on Chrome in full screen mode. It's usually a little bit faster. Okay, so it's almost finished. Okay, now we get the tetrahedral mesh of the whole volume. So now let's just extract the tet mesh, and here we can just use the default one in numbers since the mesh was nice, and we can try to plot. So here we're getting TV and TT, which are the tetrahedral vertices, and the tetrahedral faces TT. So this is the mesh we get out of it. And you see here a nice side effect or feature of Tetwile, which is automatically coarsen and generate a mesh which is nice, even if the input was so full of faces like here. So we get a tetrahedral mesh which is much coarser. We can control also the resolution. So now the next step is, well, we want to specify the boundary condition. And here we want to do something fancy. We want to, for example, attach this part here, and we want to move this other part here. So we cannot rely anymore on automatically selecting faces next to the bounding box. What we want to use is to use a function, a lambda function, to select them. So before that, we can just load the mesh into Polyfem, and we get this mesh with the bounding box, so everything is good. So for the side set here, what we want to do is just get the bounding box of the mesh using SciPy. We're getting V and F, so this is the input mesh. And now what we have here is just a function that takes a point of face barycenter, and it returns a number depending on which side set it is. So here I'm just creating a function which first selects if the barycenter in Z, here, coordinate 2, is close to the Z of the minimum of the bounding box. And then if the Y is larger than the center, it means it's the top part of this flat region, it's 2, and otherwise it's 1. Let me just execute this cell. So now we can just set the side set using the function we just defined, and then as in the 2D example, just get the side set out of it to verify if everything is correct. So here we don't see anything, but what I did is just creating an array of color which is 0, and then set the value to 2 where it's 2, and 3 to where it's 3. And you see here everything here is violet, so 0, and then we have 1 and 2, so green and yellow, appearing here for the faces we select. So this is again a sanity check. When you set your side set, it's always important to actually plot them and be sure that you actually selected what you want. In normal software, normal finite element software, you do that through clicking on faces. And another important thing is to check if your selection didn't leak on some faces you don't want. And in this case, everything is nice and kosher. So now that we have the side set, well, it's exactly as before. We just created a problem. We can set the PDE here, select some material parameter. Here I want some rubber to deform it better. And then we can just set some force on 2, which is, set some displacement 0 on 2, which is the bottom part, and apply some force on the top part. This is exactly as what we had before. It has different indices, but it's exactly the same way of solving it. And now, as before, where we can just solve it, I put some more, I mute the logging because it will be too verbose, and now we get the solution. So it takes a little bit of time, and now we can just visualize the solution. And this is again the same plot we had before. So I'm just getting the points, the tetrahedra, and the displacement. And now I'm not visualizing anymore the Fomizi stress. I'm visualizing the norm of the displacement, and at the very end I'm just displacing the vertices and visualizing the mesh like that. And now you see everything here is nice, and we get this nice deformed solution. So now what about if we want to do some fancy visualization? Let's say, for example, visualizing the isolines of this displacement field. So I told you that in PolyFam the solution is actually upsampled because you may use a higher order element or because your geometric mapping may be not linear. And because of that, every element in this tetrahedral mesh is completely separated and disconnected to the next one. So every tetrahedron is on its own. So if you want to visualize isoline, well, there are several steps we need to take. The first one is we need to merge all these tetrahedral together. Then we need to extract the surface, and then we can actually extract the isoline. So the first thing is to remove the duplicate vertices to stitch everything together. We can just use NumPy. We can just use NumPy unique, and this returns us the unique points. So we use P. So P was the solution here, the sample solution. To give us the new points, the unique points, but also the mapping, the indices and the inverse mapping. So we can use that, for example, to select the faces or select the displacement or the coloring. So like that, we obtain a mesh which is now all stitched together with just 3 lines of NumPy. And this is again one of the power of using NumPy as a glue, is that now you have the full power of different libraries like NumPy or even PyTorch or TensorFlow. So now we want to extract a tetrahedral mesh, so we can just use IGL to get the tet-tet adjacency. So this is a function that returns us an adjacency list. So it tells us for every tetrahedron which other tetrahedron is adjacent to it. And there is a convention is that if adjacent to that tetrahedron is -1, it means there is no one. So here what we'll be doing is just going over the adjacency list, going over all the faces of the tetrahedron, get the face, check if the adjacency list of that face is -1, it means it's a boundary, there is no one on that size, and we just append that face to the list, to the surface face. And in the very end here, we're just converting that list into a NumPy array. We execute that cell. So this is just a loop to extract the surface of a tetrahedral mesh. So now we get the faces of the two tetrahedral mesh. So the final thing we just need to do is just get the isolines, and for doing that we just call IGL isolines. And on what? Well, on some points, the surface mesh and the color we want. And in this case we want 20 isolines. And this will return us a list of points and lines in 3D. So let me just call that. So now we have the points and the isolines. So now we can finalize the visualization. So here I'm just visualizing the surface mesh for efficiency reasons since we have it. And then I'm just adding edges, and well, the edges will be iso P. So this is the points we just calculated, and iso L. So this is the final visualization, and we see here nicely the isoline of the displacement field. So again, you see with some few lines of Python, we can go from loading a mesh into generating a tetrahedral mesh, run a finite element simulation, and then manipulate it with NumPy and libIGL to get, for example, isolines. Thank you for listening. That's it on my side.